Hello everyone. In the lecture today, we will continue the introduction about the topics in traverse computation. In our previous lecture, we learned how to use the coordinates to adjust the moments. In this lecture, we will focus on applying the coordinates for the estimation of the moments. First, let's see how we can use the rectangular coordinates to identify the linear line in the coordination system. Assuming that there is a line started from the point I with the coordinates of xi, yi, and it ends at point j with the coordinates of xj, yj. Also, there is one point in the line. We set the coordinate is x and y. Then we can identify the line based on these coordinates. We know that for this line, the slope of the line is consistent. With that, we can use the definition of the slope to identify the relationship between the coordinate of x, y with respect to the 2 points I and j. For the slope, we will have y minus yi divided by x minus xi. This is one definition based on the point of I and the point in the line. Also, we can define the slope based on the start and end point, which will give you the value as yj minus yi divided by xj minus xi. With that, you can further derive the relationship between x and y, which will give you y minus yi times xj minus xi equal to x minus xi times yj minus yi. We can further simplify this equation as yj minus yi times x plus xi minus xj times y plus xj yi minus xi yj equal to 0. With that, we can simplify the equation here with some constants. That is ax plus by plus c equal to 0. Here, by comparing these two equations, we can define a as yj minus yi, b equal to xi minus xj, and capital C equal to xj yi minus xi yj. So we can use these three constant values and the variables x, y to define the line in this figure. In addition, if we extend this line in these coordinates, we can find that the line will intersect with y-axis and the length here is letter b, and also it will interact with the x-axis and the length here is letter c. In addition, we will have the angle between the line and the y-axis. For these three variables, we can actually define them based on the three constants in that equation. For letter c, it equals to minus c over capital A. This is actually comes from the situation when y equal to 0. if you assume y equal to 0 in this equation, you can see that little c equal to minus c over a. Similarly, if you assume x equal to 0, you can find out the value of little b, that is minus c over b. For these two equations, here the value of c on the right comes from the equation on the left. In addition, for the value of the angle aij, we can find that the value of tangent aij equals to minus b over a, which is just the slope of the line. Now let's check one example to see how we can use the rectangular coordinates for the identification of lines. In this example, we want to find out the coordinates for the intersection of the line passing from the station 1 to 3 with the line going from the station 2 to 4, and the coordinates of the 4 stations are shown in the table below. In the table, we can find out the x and y coordinates for all the 4 points, and the value in this table is actually very large, which will make the computation very complicated. So in order to simplify the computation, we will try to reduce the number. So the way for us to reduce the number is like we will apply the reductions for both x and y coordinates. In this case, we can reduce x coordinate about 4300. For y coordinate, it could be reduced about 6000. And these two values are selected based on the values of the original x and y coordinates. And the last two columns represents the adjusted x and y coordinates, which will be applied for us to do the calculation. Then we can use the adjusted coordinates to identify the intersection of these two lines. First of all, we need to draw the two lines in a coordination system. We have x-axis and y-axis. For line 1 to 3, based on the adjusted coordinates, we have the line as shown here. For the line 2 to 4, is shown as this one. And we want to find out the coordinates of the intersection, which we assume is x prime, y prime. Then we can do the calculation. First, we will start with the line 1 to 3. We know that the intersection x prime, y prime is also on the line 1 to 3. So we can use the equation that we introduced previously. That would be y prime minus y1 equal to x prime minus x1. That is the same to y3 minus y1 equal to x3 minus x1. This is equivalent to y prime minus 150.82 divided by x prime minus 82.09 equal to y3 is 215.76 minus 150.82 divided by 756.06 minus 82.09. So that's for the line 1 to 3. for the second line from 2 to 4. We also know that the intersection x prime y prime is on the line 2 to 4. So we will have the similar equation applied. That is y prime minus y2 divided by x prime minus x2 equal to y4 minus y2 divided by x4 minus x2. That is y prime minus x2 is 36.90 and x prime minus y2 is 470.93 equal to 347.30 minus 36.90, 485.69 minus 470.93. By solving these two equations, we can find out the value of x prime y prime as x prime as 478.16, y prime is 188.98. Then for the true coordinates, before the adjustment of the entire coordination system, we will have the true value as x equal to x prime plus the adjusted value 4300, and for y that will be y prime plus 6000, which would be the value we applied for y coordinates in the previous page. So that's the way for you to find out the coordinates of the intersection. We can also use the coordinates to calculate distance from one point to a line, which is also the perpendicular distance from the point to a line. In the figure here, the distance from the point to the line is shown as the value of little d, and the dashed line should be perpendicular to the line of I to j. So we want to know what's the value of d. In this kind of problem, we are given the line from I to j. We know the coordinates of the 2 points I and j. Also, we can write the line as the equation ax plus by plus c equal to 0. Moreover, we are given the coordinates of the point P, that is xp, yp. We want to find out the value of the perpendicular distance, little d. The calculation about the value of d is very complicated. So here I want to introduce the details. I will just show you the equation for you to calculate the value of d from one point to a line. So the solution is d equal to a divided by plus minus square root of a squared plus b squared times xp plus b over plus minus a squared plus b squared times yp plus c divided by plus minus square root a squared plus b squared. Here you will see that the three coefficients in the equation all have the uncertain sign plus minus, and we need to identify the sign for each coefficient. In order to identify the sign, we need to know the angle between the perpendicular line, which is the line from the point P to the line ij, and the perpendicular line to the horizontal line, which we define as the omega. With the value of omega, we can simplify the equation as xp times cosine omega plus yp times sine omega plus b times sine omega. You need to use the sign of these three values to identify the sign for the three coefficients. In addition, for the value of little b in this equation, is the intercept of the line ij to y-axis, and the value of b is defined in the previous pages. Now let's check one example to see how we can calculate the distance from one point to a line. Here we will use the data as shown in the example 1. We want to find out the distance from the point 6, which we are given the coordinates of this point, to the line 1, 2, 3. First of all, we need to identify the locations of the point 6 and the line I1, 2, 3 in the coordinate system. We have x and the y-axis, and we are given the line 1, 2, 3. Also, by the coordinates of 6, we can find out 6 is on top of the line. And then we want to find out the distance from 6 to the line 1, 2, 3, which means we need to find out the perpendicular line to the line 1, 2, 3. And the distance of this perpendicular line is the one we want to find. In the solution, we first need to use the equation to identify the line 1, 2, 3 based on their coordinates. That is ax plus by plus c equal to 0. With the coordinates of 1 and 3, we can find the value of a as 64.94, b equal to minus 673.97, and c equal to 96,317.23. In the second step, we want to calculate the value of the square root of a squared plus b squared for the calculation of the value for the distance. With the value of a and b, we can find out the square root as 677.09. Then we need to identify the angle between the perpendicular line and the horizontal line, which would be the angle shown here. We can find that this angle is between 0 and 90 degrees. Then we can get sine omega is positive, also cosine omega is positive. With this information, we can then calculate the distance from the point 6 to the line 1, 3. So we have d equal to a divided by plus minus a squared plus b squared times xp plus b over plus minus a squared plus b squared times yp plus c over plus minus a squared plus b squared. This also equals to xp cosine omega plus yp sine omega plus letter b times sine omega. From the third step, we know that both sine and cosine omega are positive, so they are all positive, which means we want to make sure that these coefficients are all positive. We know that a is positive and the square root is also positive, which means we can choose the positive sign here. For the second term, we know b is negative and we want the whole coefficient to be positive. Then we have to choose negative for the part in the bottom. And similarly, c is positive, then we will just choose the positive sign for the square root. And with this information, by the selected sign for the square root in the equation, we can find out the value of the distance as 167.55. So that's the way for us to find out distance from one point to another line. The most important thing we want to do in the calculation is to find out the right sign for each coefficient. Next, in the surveying about the route and the property boundaries, for a lot of situations we want to use a smooth curve to connect two straight lines, which means we need to know the description about a curve with the coordinates. And this one is related to the expression of the coordinates for a circle. The figure here shows the information we need to use for the description of the circle based on the coordinates. Assuming that the center of the circle is O and we have the coordinates as h for the horizontal axis and k for the vertical axis. And for any point along the circle, we can express it as x minus h squared plus y minus k squared equal to r squared. Here, the value r is the radius of the circle, and we can use this information to describe any points in the circle. Now let's check one example for the implementation of the circle. In this example, we are considering the route and the property survey. Usually, it's necessary to determine the coordinates for the intersection of the straight property line and the curved center line or the property line in the route and the property survey. In this example, we assume that the curved property line with the radius of r equal to 750 meters. It's intersected by the line QR, which is the center line of the serial right-of-way. The azimuth of the line QR is 30 degrees 50 minutes and 0 seconds. It wants us to find out the coordinates of the point P, which is the intersection of the curve and the straight line. We also have the coordinates of the point Q and O. Here O is the center of the circle. To solve this problem, we first need to summarize all the information provided. First, we will have the circle with the center of O, and the radius is R. Let's draw the circle. In addition, there's a straight line from Q to R. And we know the azimuth of the line, which is AQR. We want to find out the coordinates of the intersection between the straight line and the circle, which is the point P. So basically, we are given the coordinates of O, Q, and the azimuth of QR. Also, we have the radius of R, and we want to find out the coordinates of P, that is XP, YP. For the solution, first we will list the expression for the circle. We know the coordinates of O as HK, which will give you the circle as XP minus H square plus YP minus K square equal to R square. The equation is applied because P is only circle. Moreover, for the straight line, we have YP minus YQ divided by XP minus XQ, which is the slope of the line Q to R. By giving the azimuth of the line AQR, we can find that slope is a cotangent AQR. Then, by solving these two equations, we can find out the value of XP and YP as 2487.258, and YP is 2856.813. For the solution, you can either solve it by hand or use some programming language or Excel to find out the exact value. The other topic we want to include in this lecture is the omitted amendment. Well, for the traverse surveying, we are missing the amendment of one or multiple segments. The first scenario we want to consider is the unknown length and direction of one side for the traverse with a polygon. You can take a look at the example here for a 6-side polygon, where we assume that the segment of 3 to 4 is missing, and we measured the departure and the latitude of all the other 5 segments. Based on this information, we want to find out the departure and the latitude of the missing segment and the distance of it. Actually, based on the property of the closed loop traverse, we can know that the summation of the departure for all the segments will be 0, and it's also applied for the latitude. That is x12 plus x23 plus x34 plus xk k1 equal to 0, and for latitude we have y12 plus y23 plus y34 until yk1 equal to 0. If we are missing the segment ij, then we can find that the departure of the segment ij equal to the negative summation for the departure of the other segments. Similarly, for the latitude of the missing segment, it equals to the summation of the latitude for the other segments. And with that, we can find out the direction of the segment I to j. We have the value of tangent aij, which is the azimuth of the missing segment, equal to minus summation of d divided by minus summation of l. Also, we can estimate the distance as dij equal to the square root of the summation of d squared plus the summation of l squared. So that's the way for us to handle the missing segment for one side. Now let's check one example for the traverse within the triangle. Here we are missing the segment 1, 2, 3, and we know the departure and latitude of the segment 1 to 2 and 2 to 3. That is x1 to 2 is a minus 3, x2 to 3 is 4, y1 to 2 is a minus 2, and then y2 to 3 is a minus 1. With that, we can find out the departure and latitude of the segment 1 to 3. So we have the value as x31 equal to minus the summation of x12 and x2 to 3, minus 3 plus 4 equal to minus 1. Also, we have y31 as minus 2 minus 1, that is 3. Also, we can find out the value about the azimuth. We have tangent A31 as minus 1 over 3, that is negative 1/3. For the distance D31, it equals to minus 1 square plus 3 square. That is square root of 10. So that's the way for us to deal with the segment with one side is missing. In the second scenario, we assume that the length of one side and direction of another side are missing, which is shown in the scenario here. In this figure, we do know the length of the segment E to D as D, and we know the direction of the segment A to E, but we don't know the direction of the segment E to D and the distance of the segment A to E. We want to find out these two values. To solve this issue, we first need to find out the information of the segment A to D, including its direction and distance. So that's the first step. Find distance and direction of dA. This one can be solved by the equations in the first scenario, where we have tangent ADA equal to XDA, that's the latitude, the longitude, over YDA. Also, we have the length of the segment A to D as f equal to square root of x dA square plus y dA square. In the second step, we want to find out the angle between the line A to E and A to D. Say this is alpha A. We have alpha A equal to the azimuth of the line A to E minus the azimuth of the line A to D. In addition, we assume that the angle of AED as alpha E. Then based on the property of the triangle for AED, we have sine alpha E equal to f is the length of the segment A to D, divided by the length of D to E, that is D, times sine alpha A. So we are able to identify the direction of E to D. And then for the distance, which would be the distance of the segment A to E, that is letter E, it's f times sine alpha D, which is the angle here, divided by sine alpha E. It also equals to D times sine alpha D divided by sine alpha A. So these two are the equations for us to identify the direction of the line E to D and the distance of the segment A to E. However, the solution in the previous page is not unique. There may exist two possible solutions. For example, if we consider a similar example, we have the 5-side polygon A, B, C, D, and we know the direction of the segment A to E, and we know the length of the segment D to E. It's also possible that we can find out another segment about D to E with the same distance. So there are two possible solutions for this case. The third scenario we will consider is the case that we are missing the distance of two or more segments, and those segments are not adjoining. With that, we are able to find out a unique solution if the lines are not parallel to each other. But if they are parallel to each other, then it's impossible for us to find out the unique solution. We can take a look at one example to see why is this case. For example, we are considering a 5-side polygon. Similarly, we have the segments B, C, D, and the segment A to E are measured. We know the direction of the segment D to E and B to A. In that case, we are able to finalize the distance from A to B and D to E. This works. However, if we consider the scenario and the missing segments are parallel to each other, then it's possible that we can get an infinite number of solutions. We're able to find out in the segment A to E here or some place here. So this is not working. If the traverse is completed for a triangle and we are missing the length of two sides, but we know the directions of these two sides, then we can still identify the two missing sides. Let's take a look at an example here. For the triangle, we know the side of A to B, but we don't know the third point C. Well, based on the measurements, we are provided with the direction of A to C and the direction of B to C. Then the intersection of these two directions would be the point C. And then we can identify the segment of A to C and B to C. So this scenario works for us to find out the exact information of the two missing sides. Similarly, for the survey with the triangle, if we are given the distance of the two sides, but the directions of the two sides are unknown, then it's possible that we will get two solutions. For example, if we consider the segment A to B, and we know the length of A to C and B to C, then it's possible that we can find out the point C below, or we can find out the point C on top. So in this case, we cannot accurately identify point C, so it's not working. So that's all about lecture today. Thank you very much. With that, we finished all the contents about the computation for the segments, including the distance and the directions. In the next lecture, we'll focus on the calculation about the area.